Hi and welcome to another Chemistry the Right Way with me, Mr. Wright, and today we're going to be talking more about nomenclature and the naming of chemical compounds because it is a subject that people who are new to chemistry, the students who are new to chemistry, often get confused, and quite frankly it's just a language that chemists use to talk to each other, and so if you can't get this bit, you'll never have access to that beautiful, beautiful world that is the world of chemistry. You've got to remember that in terms of chemical names, there are common names. The common names are the types of things you get at grocery stores or at hardware stores. And then there's old names. Sometimes these are very old names. And then there's the modern form of the actual chemical name. And so that's the piece that we're going to be focused on, right? The piece that we're going to be focused on is the kind of name that you would get maybe on the back of the ingredients list on the bottle, not something that was published in literature 100 years ago or has a common name that you would find, again, at that grocery store or the paint shop or something like that. So with that, we're going to be talking today about naming metallic compounds. So the first thing you have to know is there are, in inorganic chemistry, so we're talking about the chemistry of non-carbon based chemical compounds. So that's a bit that you kind of have to wrap your head around a little bit. We're talking about inorganic, meaning effectively the rocks and minerals of the earth. That's where it gets its name from. Inorganic meant has never lived, will never be alive. Although those boundaries are always like grey and are shifting. So today we call it inorganic chemistry. Organic chemistry, which is a completely different set of naming rules. Organic chemistry used to be the chemistry of chemicals found in living systems. And then very famously in 1878, I think it was, a chemist called Wohler in Germany managed to synthesize a chemical, managed to make a chemical out of non-living things that previously had only been identified as coming out of living things. And that's kind of where the lines got blurred. And so now we just say organic chemistry is all about the chemistry purely of carbon. Anyway, let's focus on this stuff. Naming metallic compounds. So the first thing I'm going to say is every single rule that I'm going to be talking about today is just about a chemical with a metal in it. So you got to remember that on the periodic table of elements, there are today we kind of consider that there are 118 elements, although those last few are still a bit sketchy. But of that, only a small proportion are non-metallic. The largest group of elements, there are more types of metals than there are anything else. And typically your periodic table is going to have a borderline on that. So periodic table typically, right? Looks like this, goes up, looks like that, got that bit right there, comes down, and then you got this weird bit at the bottom, we'll talk about that. That borderline goes like that, right? So you got boron right there, and you got aluminium right underneath it, right? And then it goes like that, pretty much, right? All these are metals, and these. Okay, this bit has its own naming rules. This bit has its own naming rules. So that's what we're talking about. We're talking about things with metals in them. Everything over here. Point being, there is one bit here, and that is right here we have the element hydrogen. Now, the International Union of Pure and Applied Chemistry has placed hydrogen in group 1. Group 1 is typically referred to as the group 1 metals. This guy has a set of rules kind of his own. He's named as if he's a non-metal, but has some of the behaviors of a metallic compound. It's complicated, but just be aware, hydrogen does not come under the metallic naming rules, even though I believe it is actually a metallic element. And I believe that with very, very good evidence. It's not just something I made up. Okay, so binary chemical compounds that contain a metallic ion. So first of all, you've got to remember we're talking about anions and cations bonding together here in order to form a neutral compound. The anion is the negative, the cation is the positive. So one of the things that makes metals metals is that they always form, or they can always form cations. So we're talking about that. So binary. That's the first thing we have to do, is we have to take a look, and what we're talking about here is two types of elements. Okay? Of those types, one must be a metal. And we're talking about a metal cation. So that means that there must be another anion, and that's typically going to be like non-metallic, right? Because that's what non-metals do. They form both anions and cations, but it's going to be a metal and a non-metal bound together. Now, sometimes people refer to these as ionic compounds. Hate that term, but you'll see that in some texts. Again, with good reason. I just don't like that ionic versus covalent compound naming, because truth is, bonding is a lot more complicated than that. So I want to go back to this first part and talk about types, because when we talk about two types of elements, we don't mean two quantities of elements, right? So I'm going to put down my metal, M, and then my non-metal, I'm just going to choose an X, right? And then I'm just going to choose variable, right? This is going to be A, and this is going to be B. It doesn't matter what numbers A and B actually are. Not at all. So we can see a really simple binary compound is just two symbols. Only two. Just two symbols. So you have to know your symbols from your periodic table, but note this, right? All chemical symbols start in the same fashion, and that is, it's always a capital letter. So that's nitrogen. If there's another letter added on, it must always be lowercase. Now nitrogen suddenly becomes sodium. This is important because now we know the next thing is going to be another capital letter, right? If it's not, it's going to be one of those. They used to be on periodic tables about 10 to 20 years ago. There were some 3 chemical symbol elements, but that was for a very special reason, and now slowly they've been changed as they've gained recognition. Like UUO used to be on the periodic table. That's sort of unoctium. There's a reason for that. It's to do with Latin. But note this. I penalize chemistry students. My students, I will penalize for this. This is a huge no-no, right? So just drawing a large N does not make it nitrogen. This is a lowercase n. This is not a capital N in English. And because that's the language that I'm speaking, and that's the language of the students that I'm teaching, if not their first language, their second or third, but it's the language that I'm assessing them in, this is not applicable. This will not get you any credit. And this certainly won't, right? That is not sodium. So you got to take a look at this bit first. So in a chemical formula, you're going to see that capital, and then if you see another symbol, then you're going to see it's lowercase, okay? So capital and then lowercase. So we've got Na, and then I got Cl. So that's a very, common compound. Today we call it salt. Salt it's actually really table salt. There are actually many different salts. But that table salt compound is 2 types of elements, right? 1, 2. That makes it binary, which means it's going to follow the binary rules. Here's another one, right? So kind of similar to that, we could have the metal again. C is carbon. C lowercase a, it's calcium. Carbon non-metal, calcium metal. When the periodic table started out, just to let you know, non-metals were given single letters and metals were given multiple letters. But again, that got confused as they were still sorting it out. So it does stand that there are an awful lot of non-metals with single letters, metals with 2 letters, but that's not a hard and fast rule. So anyway, Ca and then Cl again for chlorine, Cl2. So my first question would be to my students, how many atoms are there? And hopefully they'd say, well, there's 1 calcium, right? The 1 is implied. Right? We never write the 1, we don't write 1x, we just write x. It doesn't need the 1, we already know there's 1 of them. So that's 1 calcium and 2 chlorines. So there's 3 atoms there, but how many types? And the answer is there's only 2 types, right? So if we get even more complicated, go further down that line, we end up with like Fe2O3, common name rust, and chemical name iron 3 oxide, but how many atoms are there? And the answer is you just add up the lowercase numbers or the small subscript numbers to find out how many there are there. And so there are 5. Right? 2 plus 3 is 5. There are 5 atoms. How many types? Only 2. An Fe and an O. All binary compounds. Okay? So our binary compounds are all named the same way. We name the metal. It goes like this, right? It goes metal, oxidation state, if we want to make that a little bit easier, we could say charge, right? In parentheses, immediately, no space. Some chemistry teachers are going to get really persnickety about this, right? So it's the metal, no space, parentheses, the charge, got to put that one in, or the oxidation state, and get this one right. This is one of those points things, right? It's the charge, and this is in Roman numerals. You need to know your Roman numerals. Brief aside. 1, 2, 3. 1 before 5 is 4. 5, 6, 7. That's all you need to know. There's no 8. Okay, so you need to know your Roman numerals from 1 to 7. Okay, we'll keep that just as a side there, right there, because I need metal, oxidation state or charge in Roman numerals, then a space. I'm going to use one of those modern like underscores you guys use. I'll just put space. Don't like the underscore. Metal, oxidation state, space, and then it's the name of the anion. And this is the big deal. It has a particular suffix, right? We're going to alter the ending on that anion. It's typically a non-metal, right? Write that in. And it is gonna have the suffix binary, always ends in "ide." Okay? Always, always, always. That's how we know it's a binary compound. We know it because it's got a metal, and then the last bit is the "ide" bit. That's like that really famous chemical ending that you come across when people make up chemicals. They'll make it up and it'll end in "ide." And that's the binary naming rule. So we're going to take a look back at those three chemical compounds and we'll name them together, right? So we started out with NaCl, then we went to CaCl2, and then we went to Fe2O3. So, metal. We can start off with that for all of them. So this is going to be sodium. You can use a periodic table, it's not a problem. Ca is calcium. Fe is iron. Remember, the symbols and the names don't always match for very, very obvious reasons for you. But if you did a little reading around the history and how these things come across, it's kind of interesting. And typically when the name and the symbol don't match, the reason is because they're named after Latin or Greek names. So we say they've been known since antiquity. So iron was even mentioned in the writings of Homer, and sodium comes from the Roman natria, meaning salt. Ferro, by the way. Calcium, that works. Okay, so next bit, open parentheses, open parentheses, open parentheses. And now I have to do my oxidation states. So if you remember, sodium's a group 1 metal, so it only has 1 charge, +1. Calcium's a group 2 metal, it only has 1 charge, but you can see we can use the crisscross rule in all of these cases. The 1 on the chlorine becomes the 1 here, 1 on the sodium becomes the 1 there, right? The crisscross rule. Calcium, group 2, can only take a +2 charge, okay? And then -1, see how that balances? 1 at +2, 2 at -1, so that makes sense. And if we go back over here, we use the crisscross rule again. The numbers are different. I get +3, I get -2. And if you remember, -2 on an oxide is always a good start, just like -1 on a chloride. Okay, so I'm going to go ahead and I'm going to have sodium 1, close parentheses, calcium 2, close parentheses, iron 3, close parentheses. And then I'm going to use my anion name, but I'm going to alter the end of it so that it takes that I form. So in these two cases we have chlorine, chlorine, and when it becomes an anion in a binary compound, that ene is converted to ide. So sodium 1 chloride, calcium 2 chloride. Iron 3, this is oxygen, oxygen. And this is where you get those like irregular verbs, right? So oxygen just becomes oxide. It's relatively straightforward. You know, phosphorus becomes phosphide. What else can we say? Bromine becomes bromide. Sulfur becomes sulfide. It's relatively straightforward. The trick to it is just to remember you have to use that cationic charge, the charge on the metal. Now, some of you may have gotten a little further in advance with this. That's going to be on the next one or the one after, when we'll talk about when you cannot use sodium 1, calcium 2. There is a shortcut, but before I give that away, I just want to stress that with my students, I always say, let's learn the rule before we learn the shortcut. Okay, one thing at a time. This is enough for most students to master before we then go ahead and start adding in shortcuts. So do yourself a favor, obey the rules at first. They're all technically correct if they're not what you could say commonly used. But know the rules before you try and break them. And then keep on subscribing, keep liking, keep doing that, keep up with the channel. And thanks very much for downloading. Do all that social media stuff if you could, that'd be great. Awesome, thanks. See you next time. Bye.